A Norman window has the shape of a rectangle surmounted by a semicircle. If the perimeter of the window is 30 feet, find the dimensions of the window that admits the greatest possible amount of light.
So we read this problem and we had a few questions and assumptions. Our first question was, what does surmounted mean? So just to verify what that means, we looked it up and we found that it means to kind of place on top. So our semicircle goes on top of our rectangle. We assumed, because they use the word perimeter, that we are that 30 feet measurement was just referring to the distance around the window and not including the fourth side of the rectangle. And then we also assumed when they ask for the find the dimensions of the window that admits the greatest possible amount of light, that we're assuming that means to maximize the area.
So because this is the shape that we are assuming, we knew that the circumference of the semicircle would be pi r, and we knew that the perimeter of the rectangle minus the top of the rectangle would be 2w plus L. We called this the length of the rectangle. And then if we wanted to also have an alternative for calling this length, we could also talk about it in terms of the radius of the semicircle. So you can also call L 2r. So you'll notice here in our perimeter formula we have 2w plus 2r. So using those, we know that we have 30 feet for the perimeter of our window. So the perimeter, 30, is equal to the circumference of the semicircle plus the perimeter of the rectangle. Now, you'll notice that the next step was to solve this equation for W, because then we can use that in our area formula.
So moving over into the rest of our question, where it asks us to find the relationship for the side lengths of that perimeter, what's going to admit the most light, which we said had to do with area. We took the area formula for the semicircle, and we're adding it to the area of the three of that rectangle, where we're only using the part in the middle. The fourth side that we eliminated has nothing to do with that area, but we rewrote it as, instead of the length times width, we put it in as the 2r with that relationship to the semicircle in relation to that width. So we put back in the part that we solved for W, so that way we don't have more than one variable that we're solving for. So when you actually go ahead and put that back in, and then finally we plug that into Desmos, so that way we could, for the sake of time, find the maximum area in relation to that radius. And we found that that maximum area was going to be 63.01 feet squared in relation to a radius of 4.2 feet.
We decided this was a good model and a good graph, which kind of led us to give a reasonable domain of 0 to 8.401, not including those in values, because as our horizontal axis is our radius measurement, as we moved away from the max towards the first zero, our radius got smaller, which for our figure would mean that it got taller and skinnier, and as our R got to 0, then it wouldn't have any area at all. As we move from the max to our bigger x-intercept, which would be bigger R values, would mean that our image would be getting wider and squattier, and so eventually the rectangle would have no area. That also kind of reinforced our reasonable domain and made us feel more confident about our solution.
So to answer our question of what dimensions the window needed to be to admit the greatest possible light, we took that radius, which we attributed to the width of our rectangle of 4.2 feet, in relation to the length of that rectangle, which would be 2 times that radius, so 8.4 feet. And then the area of that semicircle would end up being 13.2 feet, which would admit the greatest amount of light in relation to the original perimeter that we were given.